Okay, welcome everybody. I hear we have a big crowd today to hear our speaker, Dr. Lucas Mensch. Will be so welcome to our webinar series. Let me just introduce myself and then I'll introduce Dr. Mensch. I'm Nancy McMillan. I'm a data science research leader at Battelle Memorial Institute, but today I'm acting as the chair of the affiliates committee for NIST and the co-chair of the industry subcommittee, which is running this series, the AI Statistics and Data Science in Practice webinar series that Dr. Mensch has graciously agreed to speak in. The purpose of this series is to provide participants with exposure to and understanding of how modern data analytic methods are being applied in real-world scenarios across various industries. We do both theoretical insights, practical examples, and discussion of issues. So today, our speaker is Dr. Lucas Mensch, who's an associate professor in the Department of Statistics at the University of Pittsburgh. Prior to his current position at University of Pittsburgh, Dr. Mensch participated in the 2015-2016 program on statistics and applied mathematics in forensic science at the Statistics and Applied Mathematical Sciences Institute, SAMC, for most of us in the statistics profession. He obtained his PhD from Cornell University in 2015 and an undergraduate degree in mathematics from Bucknell in 2010. Dr. Mensch's primary research lies at the intersection of machine learning, statistical learning theory, and traditional statistical inference, specifically developing formal procedures for learning algorithms to improve the interpretability and inference capabilities of these otherwise black box methods. Some of Dr. Mensch's best known work is on random forests, a topic he'll be talking to us about today. In addition to Dr. Mensch's methodological work on random forests and other machine learning methods, he's applied these methods to a diverse array of applications, including ecology, medicine, sports statistics, law, policing, and forensic science. So allow me to introduce Dr. Mensch, who's going to be speaking to us about random forests, why they work, and why that's a problem.
All right. Thank you very much, Nancy, for that very nice introduction. And thanks for the invitation to speak to you all today and for you all to coming. This is a great turnout. Let me go ahead and share my slides and make sure this comes across. Everything look okay on your end? Okay.
Yes, it does.
Okay, thanks. All right. So this is work that I did a few years back with one of my, let's see, former graduate students and soon to be former postdoc at Emory, CU Joe, and also job market hopeful this year. So if you see him, see his application floating around, give him a look. He's a good guy. This was all sponsored by the National Science Foundation. So I have the talk broken down into three parts. The first part is kind of background and foreshadowing. Um, this is kind of setting the stage for well, I guess it's reviewing some of my earlier work, but it's also setting a stage for what's to come sort of at the end of the talk. And so in particular, I'll mention some of the applications that we worked on kind of early in my career. And I'll mention one problem in particular that goes all the way back to my time as a PhD student that at the time we kind of found a solution for relatively quickly and didn't sort of think anything odd about it. But hopefully you'll see by the end of the talk some new insight on where that problem was coming from in the first place. And then parts two and three are sort of the meat of the talk. So the talk's called Why Random Forest Work and Why That's a Problem. So part two is the why random forest work part. So I'll talk a bit about model complexity, degrees of freedom. We'll get into this idea of randomization as regularization. And then in part three, we'll look at what I think is the most interesting part, and that's sort of why that's a problem, why this presents challenges for doing inference in the realm of machine learning, why this introduces a whole host of problems for a lot of commonly used techniques for methods in predictive inference and similar things for things like variable importance. All right, so I'm guessing that most of you, if you're in a webinar like this, are probably at least somewhat familiar with random forest. But here's sort of a quick 1 or 2 minute overview for anyone who just needs a quick refresher and to make sure that we're all on the same page. So this procedure goes back to 2001 when it was introduced by Leo Breiman. For the purposes of today's talk, I'm just going to assume that we have data in the form of ordered pairs, these x's and y's. X's are the features. We'll say we have P of those. Y is the response. Um, for the purposes of today's discussion, we can just assume that Y is real valued. It doesn't technically need to be real valued for a lot of this theory underlying all of this to go through, but just to give you something concrete to have in mind, you can just think of it as being real valued. And then we'll just assume this sort of typical generic regression relationship where Y is some function of the X's plus epsilon. So when I say the term random forest, kind of in its most general form, you can think of this as just encompassing estimators that take on this general form. So we'll assume that we're taking B resamples of the original data, building some kind of usually randomized base learner or otherwise model on each one, and then taking the average across all of them. So if we're given some point X where we want to make a prediction, we take that X, we plug it into some function. Let's call that T. You'd normally think of this as a tree. So X is the place where you want to make a prediction. This script DN is the original data set. And then theta just would encompass any and all randomness that goes into the procedure. Um, so that equation that I just showed you is kind of a generic form of random forest. This is the form that you'll typically see defined in a lot of research papers that deal with sort of theory and methods work related to random forest. The specific version of random forest that was introduced by Leo Breiman in 2001 had a lot of those things more specifically drawn out. So in that case, and in the case that's normally done in practice, the resampling is done via bootstrapping. The base learners are typically just cart style trees. The trees are typically fully grown or near fully grown. And when we're talking about random forest specifically, this randomness that I had in theta here, this would be assumed to encompass two things. One would be the resampling itself, so drawing those bootstrap samples, and then there's also this other source of randomness, which is this mtry parameter. And so this will be a key focus of what we get into today, the idea of this mtry parameter and what it's doing. There's sort of two different ways to define this. The most standard way of defining it is just to define it as an integer between 1 and p. And this will just define the number of features that are randomly made available for splitting at each internal node of each tree. And so as you're going through and building these trees, as opposed to typical cart style trees where you would look through every feature and just find the best place to split and then choose the best among those, with random forests, we're going to assume that ahead of time we specify some integer, mtry, where mtry is less than or equal to p. And that value of mtry just tells you how many features are randomly going to be made eligible sort of at each internal split. So the lower the value of mtry, the more random the procedure would be. The higher the value, the less random and sort of more greedy that procedure becomes. So if you set mtry to be equal to p, then random forest just reduces to bagging. Okay, so a lot of my early work on random forest, and I guess still to this day, there's still some work that I'm doing in this area, was focused pretty heavily on the inferential side of things. And so the big idea was to sort of say, okay, we have these procedures like random forest that seem to work really well in practice, that seem to be pretty robust with different data types. They're good at generating accurate predictions. And yet people don't want to use them because they're really hard to look inside. There's this black box kind of thing going on. It's really hard to go back and audit those models and understand where the predictions are coming from. And so people are nervous to use them, right? Reasonably so. Um, and so the sort of big picture idea was to say, okay, can we take these procedures that we know are already working well, and can we sort of tweak them in minor enough ways that we don't hurt the predictive accuracy too much, but we sort of pave the way for doing familiar inferential things like building confidence intervals, conducting hypothesis tests within this machine learning realm. And so to do that, one of the first things we did was replace that bootstrapping step with subsampling. And so that means that trees were built with little m subsamples, each of size k, instead of the full bootstrap samples. When you do that, that equation that I showed you before now looks like this. This looks a lot like a U statistic. It's not exactly a U statistic. In a later paper from actually just from a few years ago, we went back and kind of recharacterized this class of estimators, something that we call generalized U statistics. Um, but nonetheless, it's kind of close enough to U statistics that you can borrow from a lot of classic U statistic theory to develop similar asymptotic theory for that group of statistics. Um, and so we can establish things like asymptotic normality. Once you have asymptotic normality, you can look at things like rates of convergence. Those things can generate confidence intervals for predictions that come from a random forest. But you can also do these hypothesis tests for feature significance. And so the basic idea here is similar to a lot of other ideas that show up in the world of predictive inference. And so we can start these tests by saying, okay, we've got this set of features, x1 through xp. I'm going to take some subset S of those features, and let's say that S is that set that I want to test for significance. And the basic idea here is that I want to build one random forest that uses all of the original feature information as it originally appears, the x1 through xp. And then I'll build a second random forest, which I'm just calling RF star here. And in that second random forest, or in that second model, if you're doing something outside the context of random forest, in that second model, I want to do something to basically mute the effect of this feature set S. And so you can accomplish that in different ways, and doing that muting in different ways has different effects on the test, as I'll show you at the very end of this talk. But the idea is to say, okay, I'll build two random forests. In that second random forest, I want to basically mute the effect of S. And so if I can do that, and those predictions from each of those models end up being relatively the same in terms of accuracy, then those features in S must not have been that important. And this, again, that's kind of the core idea that underpinned a lot of the early testing frameworks that we developed. But this is also a common thing, I think, throughout the world of predictive inference. Some version of that kind of test is pretty common. In our specific case, because we were working with random forests and we had these nice kind of theoretical results to go along with it, we could develop a parametric version of this where you basically said, okay, I've got two random forests. If I can establish some notion of asymptotic independence, then I can get that predictions from each of those forests are asymptotically normal. So under the null hypothesis that those features are not significant, the difference between them should be asymptotically normal and centered at zero. And you can use that to develop various kinds of tests for importance. You can also develop tests for additivity. One thing I'll just note quickly here as kind of an aside is that this is a rare situation in which the parametric version of this test is a lot more computationally intensive than the non-parametric version. And that's because there are, number one, there are really efficient non-parametric versions of this test that we've developed in the last couple of years that don't require any kind of rebuilding of any of the trees. And the parametric versions do require pretty extensive rebuilding and re-estimating of those models because you need to estimate this covariance. And that covariance is in kind of a tricky form. All right, so this is the last thing I'll mention in the way of background. This is some of the first work I ever did with this. This goes back to my time as a PhD student. So what you're looking at here in the upper plot, this is presence absence observations of indigo buntings all across the United States in the year 2010. This was data that was collected at the Lab of Ornithology at Cornell. This was stuff I was doing when I was a PhD student. And so you can see a pretty clear picture in the top here, which is that this is a highly migratory species. These birds are kind of here in the summer and not here in the winter months. And in this plot below, you can see the confidence intervals that we developed to go along with this. So this is, a pretty standard kind of thing. We built the random forest. We applied the theory that we had developed to get these confidence intervals. Everything is looking sort of as we expected it to. And here's where the problem that I'm alluding to sort of first arose. So again, looking at this top plot, it should be, well, looking at either plot, actually, it's immediately obvious that time of the year is a hugely influential predictor here, right? This is a very highly, very obviously migratory species. If you want to know the probability of observing one of these birds, if you go out looking, knowing what time of the year it is ought to be awfully important, right? The only marker for time of the year that we had in that data set was month. We indicated that by month of the year. So any test where we just looked at the importance of month for making those predictions should show up as highly significant, right? And so again, remember with these tests, we're kind of building these two different versions of random forest, and then we're checking for a difference in predictions. Um, I guess technically a difference in predictive accuracy of those two models. So in this first test, we just tested a model that included the original version of month versus a model that did not include month. Right? This is sort of the natural thing you might first thing to test. You get a very large, hugely significant test statistic, p-value of essentially zero. Great, that's what you want. Here's the problem though. What we found was that even if you just randomized month, so even if you just took that original data set and just randomized the initial value of month, and then compared that to a data set, or compared that to a model that you built using a data set that did not include that month at all, you still ended up with something significant. And this is pretty troubling. You can see here, there's an obvious sort of, you know, two levels of magnitude drop in significance here, but it's still something that's significant by any reasonable alpha level, right? And so the next thing you might think is, okay, well, there's, I don't know, did I accidentally induce some kind of pattern when I randomized the month? So you could check maybe for a difference between one version of one randomized month versus a different randomized month. You don't see any significance there. And so the test that we ended up suggesting in practice was this last one where we said, okay, instead of uh, testing for significance by looking at one data set that includes the variable and one data set that doesn't include the variable, um, do this other thing where you include the variable as it originally appears in the initial model. And then in that second model, include some randomized version, right? So keep the dimensionality of the data set the same, but accomplish that muting in some kind of other way. Right? Again, that just have this in mind because this is going to show up as maybe something that we can garner some insight from by the end of the talk. All right. I guess that's the end of part one. All right, so getting into sort of the meat of the talk now. The why do the random forest work part? Okay, so random forests, I guess at this point have been around almost 25 years. There's been a whole lot of work done with them, both theoretical and methodological. If you're not familiar with it, there was a really, really good review paper written by Gerard Biao and Erwin Cornet in 2016. And they kind of detail a lot of this progress. They go through a lot of the methodological developments and statistical and mathematical developments that have come about along the way, the different ways that people have sort of developed alternatives to the classical random forests, these kind of things. Interestingly, though, one of their kind of big conclusions, big takeaways from that review paper is that, you know, despite having made all this progress, we still really don't understand why these things work as well as they do. So in particular, they sort of mentioned that, there's not a lot of studies that do a great job of looking at the influence of these tuning parameters. This is something that just kind of always gets brushed to the side. And then most notably, present results are insufficient to explain in full generality the remarkable behavior of random forests. And before we really dive into this, I will just stress there really is good reason to think that random forests are particularly good. If you had a whole bunch of data sets and you tried a whole bunch of methods on each one, random forests are unlikely to they're certainly unlikely to be the best on everyone, but you'd be hard pressed to find very many data sets where random forests just do terribly relative to other things. Um, so there was a paper in 2014 that did a really, really extensive study, just comparing a whole bunch of different classifiers on a whole bunch of different data sets. I don't remember the exact numbers, but there were well over 100 models applied on well over 100 data sets. And what they found was that not only did random forests rank number one overall But of the top five performing methods, three of them were just some variation on the original version of random forest.
Dr. Minch, can I interrupt
Yes,
you with a couple questions from the
sure,
audience?
sure,
Okay.
sure.
Okay, so there was a question about random forests, assuming IID data and that this is time series data, and then also a request to talk a little bit more about randomizing the time series data.
The So, I mean, I guess I would typically assume that it's IID. Um, I don't know that it's relevant for what I'm gonna get into. Um, I guess we do typically assume it in the theory that we develop, but um, I'll, yeah, I guess I should, yeah, sure. Let's just think of it as IID for the for the purposes of the rest of the talk.
Okay, and then regarding, I think this is the random, when you were subsetting in the method,
Uh-huh. Uh-huh.
how was that done with the time series data?
I'm not sure. Here. So here we're not thinking of it as time series data. We just sort of have a time indicator there. So this isn't um we're not treating this as data that comes in over time. We just sort of have an indicator for month in the data set. I'm sorry, I see now where the question was coming from. Yeah, this is just kind of we treat that feature as we would any other feature, just essentially as an indicator for month.
Okay, so very active crowd out here. So if I can continue to interrupt for a
Sure,
minute.
sure, sure. Go
This is
ahead.
back where you were. The great results for random forests seem to be pre the deep learning explosion. Would you
Yeah.
have a date on that paper? And do you think that would still hold?
Um, these
I
is
think
this
a little farther.
uh
You were talking about the three of the five top classifiers were variant random forest, and the top was a random forest.
yes, sorry.
Yes.
Here. I think those results would still hold. I don't know what they did, how much they did in terms of deep learning. I think it would be more competitive than what people would think. Um, I'll Let me actually circle back to that at the end because there's there after I sort of go through the why random forest work part of things, that'll give me the context to talk about
Okay.
that aspect, how deep
And
learning
then
might.
selection of m variables out of p variables, is it with replacement?
No, generally not. So generally you do this subsetting without replacement, I guess you could say. I don't think it would really hurt anything if you did it with replacement, but there wouldn't be anything to do with the duplicates. So the sort of big idea is just to add in some randomness there into the procedure. Um, you could actually accomplish that in different ways, but generally just think of it as being done without replacement.
Okay. And I think this question goes back to when you were looking at the months on the data. What do you mean by randomized month by some sort of permutation?
Yes, exactly. So just a permutation of months. So if you were to just essentially take that original data set and permute that column, that month column, and pretend like that was the original data set, you would still see something showing up as significant.
And can you use random forests to rank outcome variables?
Yeah. To rank outcome variables, not sure what that would mean. You could use them to rank. Maybe what they mean is, I mean, you could use them to rank variables in terms of importance. If you were talking about the predictor variables, you could use, for example, if you wanted to, you could do a test like this for each of the features, and then you could take those sort of the magnitude of the test statistic as like a reasonable measure of variable importance if you wanted to do something like that.
Okay. And then there's one more comment, and then I'm going to let you go on, and we'll come
Sure.
back to questions in a minute. There was a question about would the randomizing the months destroy the relationships with other variables?
Yes. Yes, it would. So that's a very relevant issue. That's something that comes up a lot in these testing procedures is kind of how to accomplish the muting of that. So um I would say there's kind of three major classes of ways that you could think of doing that muting. One would be just deleting it entirely from that second model. The second would be doing some kind of permutation or some kind of other um, sort of independent muting, I guess if you want to call it that. And then the third would be you could think of this as essentially like replacing that feature in question with a knockoff or something like that, something that's designed to remove the effect of that feature on the response, but still maintain at least an approximate relationship to the other features. So that's kind of going in order of validity, but also just difficulty. The last version of that, the one where you kind of do something like substitute with knockoffs, is by far the most ideal way to do that, but it's also the most difficult and computationally intensive.
Okay, so one more question that loops back to what we were talking about with the 2014 study that found the random forest as the best performing algorithms.
Yep.
And this is kind of an extension there to the deep learning question. Is there
Yep.
interest in furthering the development of deep random forests, deep learning architectures that utilize random forests instead of neural networks?
So there was actually I just saw like within the past couple of weeks there was a paper that talked about doing essentially that. Basically essentially inserting a random forest type mechanism in a neural network type architecture. I think that was done largely in the way of like smoothing and maybe a little bit for interpretability. Um, I Again, let me remind me of this and let me circle back to it maybe after part two. Why don't we do this after I'll stop again after part two and we can revisit some of these because there's um these are sort of touching on things that I think are that there'll be more intuition for after part two.
Okay, great. That's good for now. Please go
Okay.
on.
Okay. No problem. All right. So, I gotta say, okay, so right, so the big idea here, this kind of the big opening to part two, was that there's been a ton of work on random forest in the past couple of decades. There's a lot of reason to think these things really do work well and really do have some cool properties. And there's been a lot of kind of mathematical, statistical, methodological work surrounding random forest. And yet, one thing that I think most people would have told you um, outside of at least the past few years, is that we still don't really have a good sense of why these things work so well, why they seem to work as well as they do. So let's first look at some existing explanations and kind of what they offer and where they fall short. There's obviously been more than just three, but I'll just kind of highlight these three. I think that most of the others that have been put forth kind of closely align with one of these. So the first explanation we can attribute just directly to Bryman in 2001 in that original paper. So in that original paper, what Bryman argued is that you could bound the performance of any classifier or any ensemble style classifier by a function of two things. And those two things were the accuracy of the individual models and the correlation between them. And so his sort of motivation, or at least the motivation he gave in the paper for doing this, was a kind of accuracy correlation trade-off. The idea was, okay, if I've got an error function that's bounded above by two things, the accuracy and the correlation, if I can decrease the correlation without sacrificing much in the way of accuracy, maybe I'll get a big buyback. This is the exact same idea that we see in the bias variance trade-off. Um, when you introduce a little bit of bias into a model in hopes of getting a big reduction in variance. And in fact, this idea of trading off the accuracy and correlation, I think, is just a bias variance trade-off. It just wasn't pitched that way at the beginning. And so there's nothing wrong with this explanation. This is the explanation that you'll see in most textbooks, but I would say this actually isn't much of an explanation. This is more of a motivation. It's a good motivation for thinking about why something like a random forest might work. It doesn't really explain why it does work and why this trade-off always seems to trade off in the right direction, right? There's nothing immediately obvious that says that by introducing randomness in the first place, or even this specific type of randomness that Brian was thinking about, will necessarily always give you this hugely beneficial kind of buyback that we actually see in practice. So that's one way of things. Again, nothing wrong with that, but I would think of that as motivation rather than an explanation. The second explanation, or the second group of explanations, I'll just attribute to that review paper by Bjorn Skorne in 2016. And this is what I would have told you at that time too. And this explanation is probably the simplest, and that's just that, look, things things in nature are complicated. Random forests are capable of fitting these weird, complicated things. There you go. Nothing else really needs to be said, right? We have random forests are kind of flexible enough to fit these weird patterns. We see weird patterns pop up in nature. We see weird patterns pop up in ways that we don't think of in simulations, and so this is why we sort of see the success across this robust range of domains and things like that. And then the last explanation, the most recent one prior to our work, and also the most interesting one, I think. This was the paper that inspired at least the beginning of a lot of the work that I'm going to talk about today. This was given by Adi Weiner at Penn. He and a group of his current and former students. And they put forth this argument that random forests work well because they are self-averaging interpolators. And so if you're not familiar with that term, interpolator, it just means that this is a model that fits the training data perfectly. So as statisticians, if you have any kind of classical statistical training, that should kind of be a bit of a gut punch. You think of fitting the training data perfectly as kind of a like sort of a gross thing that you probably shouldn't be doing, because the assumption is that if you're fitting the training data perfectly, then you're probably overfitting the test data, right? You're probably overfitting whatever that true underlying relationship is, and so doing too well on the training data is probably going to lead to poor performance in the test data. And they basically argue that that's just not right. That maybe in the real world, we worry too much about overfitting, and maybe this whole issue of signal and noise isn't as big a deal as we make it. Um, random forests consist of these deep trees. Those deep trees are they're interpolating if they're fully grown. That there's some sort of technical issues there that I won't necessarily get into unless there's interest. Um, but that's basically the argument that random forests seem like they're overfitting. Overfitting seems like a bad thing to statisticians, but look, they work well in practice. How bad could it possibly be? So that paper came out 2017, 2018, somewhere around there. At the time, I had just met Siu, who you'll recall is the graduate student that I did most of this work with. Um, we were looking at that paper, and I really just had this bad, sort of, I don't know, kind of like frustrated feeling with that paper. Not because the paper was poor quality or anything like that, but just because in my personal experience, I had always sensed the exact opposite. That, if this really was just an issue of, random forest kind of overfitting, or at least being close to overfitting, and that just wasn't as big a deal in practice, then it should be that random forest worked well on nice clean data sets where signal was really easy to pull out. And yet, in my experience, it always seemed to be the exact opposite. That if I was resorting to a random forest to do some kind of model fitting, it was usually in these big, messy, complicated um, data situations. And so, one of the things that Siu and I realized as we were talking about this is that virtually um, every paper that I tried to address kind of why random forest work, or what's kind of leading to that good performance, had discussed that in sort of absolute terms. And what I mean by that is that the authors would just kind of take as an assumption in the introduction that random forests simply did work well, right? The papers were written from the standpoint of random forests work well. We know that. We take that as an assumption. Here's our theory or explanation as to why. And that's just not true. It's just simply not true that random forests do work well in any kind of absolute sense. You can't feed in junk and it just gives you a good prediction regardless. It's not difficult to find data sets where random forests perform really poorly. However, it is kind of a challenge to find very many data sets where random forests work poorly relative to other models. So if you're comparing random forest to a whole bunch of other models, you'd be hard pressed to find very many where random forests do really poorly relative to all of them. And so we sort of began this by thinking about, okay, let's not think of this as just random forests work well. Let's think of it as when random forests work well, and not just when they work well in absolute terms, but when do they work well relative to things that are close by, relative to the other models, to other models, to other modeling strategies that are very similar to random forest. Well, if you're thinking about things similar to random forest, the obvious thing to think about would be bagging, right? Bagging just being essentially a non-random version of random forest, where you're doing everything the same in the procedure, except that the trees are being built in a greedy fashion instead of doing this random subsetting idea. And so we said, okay, let's start there. Can we just think about it? Can we actually sort of try and uncover when do random forests outperform bagging? This seems like a good place to start. A simpler question. And so we looked at a bunch of linear models, we looked at a bunch of nonlinear models, and in particular, we were looking at how things change at different signal to noise ratios. So you'll see this SNR pop up a lot through the rest of the talk. SNR just means signal to noise ratio. The larger this value is, the better quality the data set is. And so show you those preliminary results. So these are some of the first results that CU generated. And these probably don't necessarily look incredible to all of you, but they were super, super encouraging to me the first time I saw them. And that is because in each one of these plots, on the y-axis, what you have is basically the difference in test error between bagging and random forest. So that means that a positive value, something up here, means that the random forest is doing better. A negative value would indicate that bagging is doing better. And on the x-axis, you have the signal to noise ratio. So as you go right on any of these axes, the further right you go, the better the data quality. The cool thing about this is that these are very, very, very dissimilar setups. So you've got a linear model here, you've got nonlinear models here, you've got very different ranges of N and P, you've got low dimensional settings, high dimensional settings, and yet, regardless, across all of those, you see what I would at least argue is a very, very similar pattern happening in each one of these settings, which is that as you increase the signal to noise ratio, so as the data quality gets better and better, the advantage that random forest has begins to die out. So if you're looking at when does random forest have the biggest advantage, it's at these low signal, high noisy data situations. And you can look at that and go, okay, that's fine, but that's still just simulations. You'll recall from a few slides ago, I mentioned that I think there was a lot of intuition all along that maybe part of the reason random forests work well in practice is because it could adapt to these sort of weird patterns that you see in practice in real world data. So you can ask, okay, well, does that same sort of thing hold? Does that same general pattern hold on real world data? If we had real world data and we imagine it being more noisy, for example, than it was, would we see a bigger advantage for something like random forest? The problem, obviously, with real world data is that we don't know what the actual signal to noise ratio is. But we do know that we could make it worse. We could just generate additional noise, tack it on to whatever response shows up in that real world data set, and we could see how random forest performance changes relative to other models as we add in more error. So that's what you're looking at here. The plot on the left, these are low dimensional data sets. On the right, we have high dimensional data sets. But again, you see the same kind of pattern here, which is that as we add more noise into the data, so this is kind of going in the opposite direction of those plots that I just showed you. So here on the x-axis, we're looking at basically the amount of noise that we're adding. But as we add more noise, the advantage that random forest has goes up. And again, you see this in low dimensional settings, you see this in high dimensional settings. This is a very cool finding. So as it turns out, you can show, and we showed in that paper, that random forests with larger values of mtry have more degrees of freedom. And so that just means that when you increase the value of mtry, those models become more data intensive. And so again, you think of mtry as just this integer um, between 1 and p. This governs how many features are randomly made available. So if there are relatively few features made available, you think of this as being a more random process. If mtry is closer to p, then this is a more standard kind of greedy process. And basically, the argument that we put forth is that when you make mtry large, sort of as you get closer to bagging and as there's less randomness going into the procedure, these models tend to be more and more data intensive, right? Um, so this is kind of, I think, a helpful framework through which you can see things, but it's also not necessarily that surprising. Um, in some sense, everything that I just showed you there was kind of a big loop around to things that maybe aren't that shocking. So the basic idea here is that um, as you make mtry smaller, for example, you're inserting more randomness into the procedure. The more random things become, the more independent the trees are going to be. The more independent the trees are, the bigger the variance reduction you're going to get. The bigger the variance reduction, the less overfitting you're going to see. And the less overfitting you're doing, the better you'd expect to perform in really noisy data environments, right? If I'm utilizing the data less, that's good when the data is really bad. That's bad when the data is really good. Um, and so we basically pitched this all through this just model complexity framework. So again, that in and of itself is not necessarily, I think, that shocking or that's difficult to understand. But what's interesting there is that that has nothing to do with trees. There's nothing about that explanation that has anything to do with trees. Um, and so, if you want to believe that explanation, or if you want to at least, sort of explore that explanation further, you should be able to push that a little bit. You should be able to take this random subsetting mechanism, this random feature subsetting mechanism. You ought to be able to sort of export it into other models. And again, if that's what's driving the performance of random forests, then when you export this mechanism into other model building methods, then you ought to see the same performance gains with those other methods that you do with random forests in the same kind of places that you see with random forests. And so the question is, do you see that with other model building techniques or not? And so to look at this, we sort of created these bagging and random forest analogs that use linear models instead of trees. So bagged forward selection is exactly what it sounds like. You take your original data set, take a bunch of bootstrap samples, uh, build a linear model via forward selection with each, and then take the average. And then randomized forward selection is the exact same thing, except that we're going to sort of insert that random subsetting mechanism into that procedure. So at each step in each one of the forward selection procedures, we will start by just randomly defining some subset of the features of those remaining, and whatever feature enters the model next has to come from that randomly predetermined subset. And so let's look at how that performs relative to other classic linear model building methods. So these simulations, the ones I'm about to show you, these come from a paper from Trevor Hasty and Ryan and Rob Tibshirani. I want to say this was maybe a 20, yeah, I want to say this paper maybe came out on arXiv around like 2017, 2018. I think it was published around 2020. But in that paper, they were explicitly just comparing Lasso to other kind of more greedy model building techniques like forward selection and best subset selection. So essentially what we did in our paper was we replicated those same kind of setups, but used these bagging and random forest analogs along with it just to kind of see how they performed relative to these other methods. So in this plot right now, you have Lasso in this kind of yellow gold color. You've got forward selection in this pink color, and you've got relaxed Lasso in this blue color. Relaxed Lasso here is just a weighted average between Lasso and least squares after Lasso. So how does something like bagged forward selection perform? You see it here, there in the red. I would argue this performs about as you would expect. So the only difference in going from in going from forward selection to bagged forward selection is that with forward selection, you're just employing forward selection on the original data as you got it. With bagged forward selection, you do bagging. You take a bunch of bootstrap samples of the data, build a linear model via forward selection on each, and take the average. So where that's going to be most beneficial, again, if you just think of bagging as being kind of a very introduction technique, then that's going to show up as most beneficial down at these low signal to noise ratios. And that's where you see kind of the biggest advantage of bagging relative to just traditional forward selection. How about randomized forward selection? So when you go to randomized forward selection, you're doing even better. And again, this would align with the explanation that I just gave you, that when you add in the additional randomness, it's reducing the degrees of freedom. So it's less data intensive, it's less complex in that sense. And so we see an even greater improved performance at low signal to noise ratios. You can see that as the signal gets higher and higher, at some point there's this crossover between the red and the green. That would be exactly the same as the crossover over the x-axis in those initial plots that I showed you. So there is some point here at which the data gets good enough that bagging will just begin to sort of outperform traditional random forests. Again, these are the linear model analogs of that, but I think the same thing holds in the tree-based setting. Um, so this these two relative to each other, the bagging and random forest, this is, I would argue, essentially what you would expect. What I didn't expect, and what's very, very cool about this, which you may not have noticed, is that this randomized forward selection, this green, is not only outperforming bagged forward selection for this sort of initial set of signals, it's doing better than lasso across the whole range of signal to noise ratios that we're looking at here. And admittedly, I didn't go into a lot of detail on this, but this is a situation that should be kind of hand tailored for Lasso to do well. This is a sparse linear model setup. This is the low setting. I think in this setting there are 100 observations. P I think is 10, so I think there's 10 total features, and I think 5 of them are signal features. So this is again, this is something where Lasso ought to be doing about as well as Lasso can do. And yet, this relatively simple, non-intuitive version of just doing forward selection, adding in some randomness and taking the average is outperforming it across all of the signal to noise ratios. But what's even more, and the kind of icing on the cake here, is that this gold bar in the background, this corresponds to an optimally tuned Lasso procedure on a large external validation set. This version of this randomized forward selection, the screen bar, is not tuned at all. We just picked this to be 0.33. So here, I'm taking mtry to be a proportion of the features available rather than an integer. So this would correspond to p over 3 if you wanted to think of it as an integer. But this is not being tuned at all. If I did tune it, could I do even better? Yes, I can. I can outperform that kind of baseline, and in fact, I can do even better. I can do substantially better than Lasso across all of these things, and I do something that's sort of close to being on par with Relax Lasso. Here's a different setting. You can see a similar kind of effect here. Again, you see sort of Lasso up here. This is a slightly larger setting. I'm going to the details here other than to say you see the same kind of things happening there.
So Dr.
Yeah,
Magic, a couple questions are building up around these plots. Can I ask those now?
Let
Wait.
me just do one more slide because that'll be the
Okay.
end of this section.
Okay.
Okay, so what's going on in all of these? What's the thing that's actually happening here? So there's actually I would argue a fairly simple thing happening here, but it's leading to this very kind of nice clean result here. And what's happening is that by doing this randomized forward selection, you're actually implicitly doing a kind of regularization. So let's think of sort of an idealized version of this. Let's think of a version where we don't do any resampling at all. We just take the same data set, we do this randomized forward selection on each one, and let's say that we build each model to a depth of D where D is less than P. So if we do that and we build a total of capital B models, then that means if we look at a given feature, let's call it xk, there's some corresponding coefficient, beta hat k, that appears in each model. And xk is either going to be in that model or it's not going to be in that model, right? If it is in that model, then under some assumptions, sort of the expected value of beta hat, I'll just write like this. Um, but if it's not in that model, then that's the same as just assigning it a coefficient of 0, right? And so when I do this, I guess here it's not bagging because we're not doing the resampling, but when I average across all of these models, I'm averaging a bunch of beta hats and I'm averaging in a bunch of zeros. And so if xk appears in alpha k of those models, then my estimate, my sort of ensemble based estimate, just looks like this, where it's alpha k times that beta hat OLS estimate. Um, so essentially, you are just shrinking this OLS estimate for beta hat. And what's more is this shrinkage factor alpha. It's going to depend on two things. Number one, it's going to depend on the probability that xk is made available in the first place, and this will be the same for all features in the model. But two, it's also going to depend on the probability of being selected once it is made eligible. And this is going to relate to its actual relationship to the response, right? How important that feature actually is. If there's a strong linear relationship between xk and y, then there's a high probability that xk will get picked once it's made available, right? And so not only do you have this shrinking, but you have this shrinking that's being directly influenced by the actual relationship between that feature and the response. Features that um, aren't that relevant, aren't that related to the response, are going to get picked less often, and so there's going to be more models that don't contain them. So there's going to be more zeros. This alpha will be less, and so what we end up doing is shrinking more on those kind of things. I'll end this section by just saying that there's a lot that can be pushed here. I didn't put much of the theory into this talk, but I have one theorem there you can read through if you want. But one of the big takeaways, one of the really cool things that we showed in that paper is that this sort of random subsetting version of building linear models is actually exactly the equivalent of doing ridge regression with a particular value of that ridge penalty lambda, where lambda is just equal to p minus m trie over m trie. Okay, Nancy, that's the end of part 2.
Okay. Can you go back to the one of
Yep,
those plots that showed a number of the models? Yes, this is
yep,
great.
yep.
Okay. So there was a question and a request for you to explain Bayes on the y-axis. Not all of
So
Bayes
it
theory, but what does it mean that it's on your y-axis?
yeah. I should probably just think of that as test error. This is kind of relative to the um optimal performance that you could have. So this is just basically a shift that's being applied. Just think of that as test error. There's nothing weird going on there. It's just a scaled version of it. We actually only did that because that's what they did in the Ryan and Rob Tibshirani's paper, and Trevor Hasty's paper, where they were looking at this. We tried to basically just copy those simulation settings exactly. So that's
Okay.
just a scale.
Okay. Are the errors all out of bag errors for the random forest, or is this something else?
No, these are actual test errors. These are test errors on a very big external test set. I want to say like 10,000 or something like that.
Vertical scale in these plots seem very
Hmm.
nuanced. So that's really a question about the practical performance difference between all these methods.
Hmm.
Um, any thoughts? I mean, the scale is very small.
Um, the scale, yeah, that's fair enough. I mean, I again, this is kind of that because it's relative to sort of the Bayes error. I mean, the optimal version would be 1, and so you're basically looking at, how much worse are you doing relative to the optimal thing you could be doing. Um, I don't actually know off the top of my head what these test errors look like on the raw scale. I can tell you, um, so we did do plots. I don't remember if they're in the paper or not. I think they are. where we tried to add sort of error bars to each one of these points. The problem with displaying that is that it gets really messy and it's hard to see like which things correspond to which other things. But I would say in a lot of these cases, I mean, the error bars are small enough that you see, a significant difference between a lot of these. Um, for example, I don't think you see a hugely significant difference between like the green and the gold, so the randomized forward selection versus lasso. But my recollection is that you do between sort of like the tuned version and lasso, if that gives you a sense of magnitude there.
So then there's also a question around the signal to noise ratio on the x-axis, and
Yep.
they like a little more explanation of how what's that representing in this data?
So here we're just looking at sparse linear model settings, and this essentially just relates to the variance of the epsilon term. So if you think of it as y equals f of x plus epsilon, this is basically relating to the magnitude of the variance of the noise, so the variance of that epsilon. If you assume that epsilon is um, normally distributed with mean zero and variance sigma squared, you could think of this as being kind of proportional to the magnitude of that sigma squared. So the more noise you're putting into it, um, the lower, I guess, the signal to noise ratio would be. So kind of inversely proportional to this. Um, Larger signal to noise ratio would mean that variance of the error is really small, so the patterns are really easy to pick out. Um, Opposite if you made the variance large. I'm being a little bit hand wavy there because we're looking at different kinds of covariance matrices and those sorts of things. But in general, that's kind of the simplest way to think of it is how much variance are you putting on the error term?
So what are your thoughts on random forests constructed with each node of each tree being a linear model built on the data allocated to that node? Would that affect or deteriorate the performance of the random forest on non-parametric data?
That'll depend. My opinion is that will depend very heavily on the signal in that data. So if you do that, if you build a linear model rather than just taking the average, then you're building a more complicated model within each node, and you're going to kind of increase the degree to which the model is depending on the data. So if the data are really good, then that'll be fine. Uh, that'll even be good if the data were like exceptionally good. But my guess is that in real world data sets, um, it's probably going to lead to more problems than it would benefits, just because I don't think the signal would be high enough. So, um, can I don't want to, do you have a good order in your head, Nancy, of questions?
Um,
I was going to revisit some of these deep learning questions, but I can come back to that if you prefer to go in a different direction.
let me scan through these one more time. I'm saving a couple of these that
Okay,
are more for later to come back
sure,
to. So people in the audience, if I
sure.
haven't asked your question, I thought we would go back for some of these. So I'm trying to keep ones that are close together here. Um, so So here's one, I think do this one and then you should go on and we'll come back
Okay,
to these others because
okay.
some of them are, other methods related. So
Yep, yep.
orthogonality can imply exchangeability of data variables. Is that true for your examples?
Um, I guess so, although I really wouldn't read that much into um kind of practice sort of direct practical application of the theory that we presented here. So it's um I don't know if you see it as a benefit or a drawback, but we essentially what we did in that paper was to say, look, we can see these like very obvious patterns going on for random forests. We can sort of demonstrate, at least empirically, this relationship between the amount of randomness and the model complexity itself. And we think that that's what's driving a lot of the performance. The problem is to show that theoretically is really difficult with any kind of tree-based models. And so we basically kicked all of the theory to the realm of linear models. Um, and so, your instinct might be to say, oh, whatever, you only have theory for linear model stuff, but you're trying to apply it to trees. The benefit, though, is that you see the same kind of pattern showing up. And so I think there's really good reason to think that those same, those same sort of relationships would hold, albeit in a less direct, probably less nice looking way. Um, but in the theory that we develop, we make kind of whatever assumptions we need to get these um, uh, sort of calculable results, I guess. Um, but we do that in part because we're not actually all that concerned in practice about the sort of linear model results, other than to show, hey, in these idealized linear model settings, you can draw direct equivalence between things like feature subsampling and other forms of kind of explicitly regularized linear models like lasso and ridge regression.
Okay, thank you. We're going to let you go on. There's more here. We'll come back.
Sure. Okay. Um, okay. Okay. So this is so starting part three now. This is, I think, is the most interesting part. Um, this is also a good time just to kind of recap basically the argument that I just made. So um, in that initial paper that's you and I wrote, as I just detailed, we sort of made this large scale argument that depended on um, this idea of regularization, and basically arguing that this inducing this, sorry, inserting this randomness induces this kind of regularization, and that regularization is really helpful when the data are really noisy. And so, um, in some sense, we were kind of arguing that, hey, random forests are working well in practice in large part because data tend to be really noisy, and random forests have this kind of built-in implicit regularizing effect where even when the data are really noisy, it's not so dependent on that data as a lot of other machine learning methods would be. And so the core of that argument was to say you're that regularization is arising by means of randomization. That randomization is coming from this mtry parameter. And so if you wanted to do more regularization, then you should do more randomization, which means you should make this mtry parameter small. That was kind of the argument. That mtry is the thing that you can do, the thing that you can make small in order to most directly affect this shrinkage proportion that I called alpha. So if you want to do more shrinkage, more regularization, you should make the models more random. That means smaller value of mtry. Um, that was the big idea, and that was fine. And so it wasn't long after we first put this paper out, maybe a week, when I started having this really kind of icky feeling about this. And I was having this feeling because I realized that it's not really mtry that's doing the shrinking. It's really the it's really mtry over p. It's not necessarily, it's not the number of features that are made available. It's not mtry directly. It's really mtry over p. Um, why does that matter? Well, you could argue, well, in practice, that who cares? You get a data set, you have your P is fixed, P is just the number of predictors. So if you wanted to change mtry over P, if you wanted to make that proportion smaller, you make the numerator smaller. But you don't need to. There's no reason why you need to. That's not an assumption that we have baked into any of the results that we had. And so, in theory, if you wanted to do more shrinking, all you need to do is make that proportion smaller, mtry over P. You naturally think of doing that by making mtry smaller, but there's no reason you couldn't accomplish the same sort of thing by simply making p bigger. How do you make p bigger? Well, one way to make p bigger is just to add in a bunch of random noise features into the data set. That would increase p, and all of the theory that we had put out to that point would have told you that that should induce some regularization. This should be good. Um, this is really troubling because that means that when you have really noisy data situations, um, we would basically be arguing that you could improve the performance of your model by simply adding in random noise features. this seems like a no-no, right? This seems like something that just shouldn't be possible. And so we thought, okay, what would that actually look like if you were going to do it? And so we put forth this idea of augmented bagging. And augmented bagging basically starts the same way that traditional bagging would. We assume that we've got original data, X's and Y's. Again, X's are the features, Y is the response. And then N is just an additional set of noise features. And the only thing we assume about N is that it's conditionally independent of Y given X. So that just means it could depend on X if you wanted to, but it can't depend on Y once you take X into account. So it could be independent of X and Y, or it could depend on X, but Y can't depend on it once you take into account X. So this is just a fancy way of saying a really simple thing, which is that suppose we did bagging, but instead of doing just bagging on the original data, suppose we just added in a bunch of additional random noise features into the model. How would that do relative to traditional bagging? How would that do relative to something like a random forest? And so we'll go through the setup for all of these, but here are kind of the first results that we had related to that. So these are all very, very small SNRs. That's something you should have in the back of your minds when you're looking at these. These are very, very small SNRs, 0.01, 0.05, 0.09, 0.14. However, these are really troubling. This plot, we'll just look at this one plot in particular to see why this is so troubling. So what you're looking at here on the y-axis, again, is just test error. And on the x-axis is just the number of noise features. So in this setup, there were 5 original features. So you could think of doing a random forest, for example, with mtry equals 1 or 2 or 3 or 4 or 5. Those are shown in the background here. So these are the results that you would get if you just did random forests at this value of mtry on that original data set. And then these lines shown in red correspond to the performance of bagging as you're adding in additional noise features. So no other randomness, no nothing. What you see here is that once I add in about 25 additional noise features, that augmented bagging idea is doing about as well as the best random forest could do. And if I continue to add in more and more and more, the model improves by more and more and more. Again, this hopefully this is coming across. This should be really troubling. This isn't supposed to happen. There's a lot of textbooks that say this isn't supposed to happen. And I want to just stress here that this is test error. This isn't training error. This is what we'd expect to happen if it were training error, right? Training error, you make the model more complex, you're overfitting, the error is going to get better. Sure. This is test error. This is error that's being evaluated again on some very large external data set. There's nothing weird or slick that we're doing here in terms of this is just test error as anyone would calculate it. So I'm just trying to stress the point that you're really seeing what you think you're seeing. This isn't due to some kind of weird way of calculating things. The models really are getting better and better as you're adding in more and more useless features into the model. Okay, so why is this a problem? Hopefully it's kind of obvious why this is a problem. But let me be specific about why this is a problem. It's a problem because there are a lot of testing procedures that have been put forward in the realm of machine learning and the realm of predictive inference that, as I alluded to at the very beginning of my talk today, that involve basically testing to see how different predictions are or how different the accuracy and predictions are between two models whenever you exclude some set of features. So for example, if you wanted to sort of formalize this a little bit, you think we have this original feature set X. If I partition that into X naught and X tests, let's say X naught, these are the features that I assume just a priori are important. X tests, these are the ones that I want to test for significance. There are a lot of testing procedures that have a null hypothesis that looks something like this. I'm purposefully giving this in sort of a generic form here because the specific versions look different depending on the test. But this is the basic idea. I'm assuming that the regression function is a function of both x naught and x test, and I want to see, could I write that as just a function of those features that are in x naught? So just basically saying, at least in terms of predictive accuracy, does X test matter or not? Are those features that are in X test, are they important or not? And again, if you recall back to the very beginning of the talk, I mentioned there's a lot of different ways to do that muting if you're comparing two different machine learning methods, and sorry, two different machine learning models. In that second model, what you want to do is mute the effects of the features. An obvious way to mute those effects is just to drop them out of the model, right? You can drop them or randomly replace them. The problem here is that if you can improve a model by just simply adding in random noise features into it, then seeing a significant result in one of these testing procedures doesn't really tell you what you think it's telling you, right? It's possible for those features, at least in theory and in those results that I just showed you, it's possible for even just random noise features to improve the performance of a model. Um, and so the next thing to see would be, okay, let's try some different versions of these tests that I alluded to at the beginning, and let's see if we actually get significant results. And we do. So here's a setup where all of the features originally were independent. I'm employing a recent version of the kind of testing procedures that I discussed at the very beginning. On the left here, I'm just calling this a drop test. Here's a replacement test. So in here, I'm comparing the performance of two ensembles, two models, where in that second model, second ensemble, I just drop the features that are important. Here, I just replace them with some randomized replacement. You can see here on the left, we see these really inflated type 1 errors, right? This is doing really bad. All of the features that I'm adding in here are just noise, and yet when I do this test, I see a significant difference. If I were to just sort of blindly employ this in practice, I would conclude a lot of the time that those features are significant. Over here, things look much more controlled. We're right near that kind of nominal 0.05 alpha level that we chose. Here's the same kind of situation where the features are correlated. Again, you see the same sort of thing. This drop test has really inflated rejection rates. The replacement test doesn't. And if you were to stop here, you might take a breath and go, okay, phew, well, at least we know just to do the replacement test, and that's the one that works. The problem is, um, in these versions that I'm showing you, these are simulations, and we know what the distribution of those features are that we're replacing. And so when we do the replacement test, we can replace the features in question with features from the exact same distribution that we already know because we're doing simulations. In practice, if I were to not know that distribution, but instead I just sort of did something simple like a permutation, or I didn't do anything to account for the different dependencies in the data, then you see the exact same kind of thing, arguably to an even worse extent. You see these, again, these hugely inflated type 1 errors. So there's a temptation here for some, I think, to just say, well, those are just bad tests then. But that's not true. There's nothing wrong with the test. The tests are doing exactly what you asked them to do. Those tests are specifically designed to measure whether there's a significant difference in predictive accuracy between these two models. And there really is a significant difference between those two models in the setups that I just showed you. The problem is um, not with the test, but with the interpretation of those tests. And so there's no problem with the tests themselves, but there is a problem with saying that just because some set of features, let's call it S, improves predictions, that S must necessarily be related to the response. It's entirely possible, especially in these noisy data settings, that even random noise features can help improve the model by a significant extent, to the extent that you will actually see that result register as significant by most reasonable hypothesis testing procedures. All right, so this was just kind of a summary of what I just said in parts 2 and 3. So that additional randomness in random forest, as we said, it offers some kind of implicit regularization. I would argue that you could see the mtry parameter in a random forest as being directly akin to something like lambda in explicit regularized linear model procedures like ridge regression or lasso. I would argue you should just look at them in similar kinds of ways. And in that latter part, in part 3, we talked about how the issue there is that regularization can be accomplished not just by limiting the value of mtry, but also by increasing p, and this can lead to a lot of issues when you're thinking about doing any kind of testing procedure. So one of the takeaways from that all of that testing related stuff that I just said, maybe the simplest way to summarize is just to say the better you can estimate the distribution of the features and their relationship to the original features that you're not testing, the better you can do that estimation, the more reliable the test is going to be. So we've in more recent papers we've compared just doing permutations, for example, to something like knockoffs. Replacing those features with knockoffs seems to do very significantly better. Um, but again, I sort of say that with a bit of caution because, how well any procedure is going to perform is going to depend on what those actual relationships are and just in general how well you can estimate them. And I'll just conclude with two kind of big picture, maybe future food for thought. One very important thing to recognize is that this is not a tree specific thing. So I talked about all of this in the context of random forest because that's the context in which we thought of and derived all of these results. But this idea of, sort of shrinkage via noise or shrinkage via randomization, it's not new. And it appears even for much simpler kinds of models. So there was a paper that came out right around the same time that our work came out, showing that this same kind of thing can happen in even simple ridge regression settings. So essentially, if you take the original data that you have and you're doing ridge regression, if you add a bunch of random noise features in that setting, it can essentially nullify the effect of doing any explicit shrinkage with that lambda. The other thing I'll mention is that there's really recent work just from a couple of months ago from a group at MIT that is sort of building on our work and saying maybe at least in finite sample settings, maybe there is kind of a bias reduction thing happening at sort of the other extreme end of the spectrum when you're looking at really high signals. That maybe random forests are also working well at that end because they're actually picking up on signals that something like um, bagging, for example, wouldn't necessarily pick up on. I will leave it with that. I'll leave this up. The rest of this is just bibliography. I'll leave those up on the screen and happy to continue with more questions.
Okay, well, thank you. And we do have more questions here. I'm going to go kind of in reverse order through them because so that they're in some order for you to help reference to the slides.
Sure, sure.
Can you explain knockoffs?
Knockoffs, I mean, you think of knockoffs as just basically it's a randomized replacement of the feature that you're looking at, um, but where you're preserving the relationships with the other variables. So this actually goes back to one of the first questions that was asked about how do you how do you generate those replacements, and don't you destroy the relationships between the other variables when you do that? Yes, you do. And as you just see, that actually does have a big effect on the testing procedure. So I mean, knockoffs is kind of a big world of literature, and there's all kinds of things you can do with them. When I say knockoffs here, I just mean replace those features in question with something that, in theory, has the same marginal distribution and has the same dependent structure between the other features as the original one does, but where you remove any dependence from the response. Obviously, in practice, you have to estimate that, and so there's a whole sub literature out there just on how you estimate those. But that's the idea that you're trying to get at. I mean, you can think of it as essentially a permutation like thing, but one in which the relationships between the other features are approximately preserved.
Um, do these results carry over to conditional forests?
Um, I'm not sure. I'd have to know the specific um, kind of forest that you're talking about. Um, I think so. I think as long as you're doing the randomization at each internal step, that regularization would still be there. I don't think it actually depends much on what you're calculating in that final node. So whether you're doing some kind of like someone mentioned earlier, a linear model, whether you're taking an average, there might not be as clean a theoretical results for those kinds of cases, but I think if you're doing that randomization at the intermediate steps, you'd get the same kind of regularizing effect. if you're talking about doing it with the testing, I know people have put forth like a conditional randomization test that has to do with trees. Um, I'd have to think about it more. I don't know, but it wouldn't surprise me if it didn't, because the tests that we're looking at here are sort of specifically designed to compare the accuracy of two ensembles. And I think I guess the simple answer, unsatisfying answer would be if they're if whatever test you're doing, if it's directly comparing the accuracy, then I would say yes. If it's doing something else where it's sort of trying to maybe bias things in some way, then it may not.
Okay. So here's one from someone I think is using some of this for their own problem. Given that the
Okay.
feature space in high dimensional data is biologically derived, how can
Uh-huh.
we ensure that augmenting it with random noise does not inadvertently obscure biologically meaningful patterns or lead to overfitting? Are there specific diagnostics or metrics you recommend to monitor this?
So I guess a couple things I would mention there. Number one is maybe I should have said this in the slides. I really wouldn't recommend doing anything like augmented bagging in practice. This is just, I mean, it's way more computationally intensive. We sort of propose this idea more as just a kind of a thought experiment and to show like, oh, you can actually screw things up just by adding in. Actually, I mean, you can make things better by just adding in random noise, which then screws up things down the line. So, unless you're in a really, really, really noisy data environment, I guess what I'm getting at is like, unless you're saying, I've already made mtry as small as I can, I can't possibly regularize or shrink more than this, then I guess you could consider adding additional features to the data set. But the data would have to be so noisy at that point that I don't know if I would trust many models to begin with. Um, I would actually look at that problem sort of in reverse. I would say if you're in this high dimensional setting where P is really big, I would be much more concerned about um, kind of spurious, not spurious correlations, but spurious findings in the sense that you may be very likely to find things that look significant simply by virtue of having them in the model. And so I would, um, if I'm doing these kinds of tests in practice, I would absolutely do something where I compared some subset of the features to another subset where or sorry, to another model where I did some kind of replacement with knockoffs or something like that, because I think that the false positive rates that you would get are probably shockingly high in high dimensional settings if you're just comparing one model versus another model where those variables are excluded. Um, I don't think you're actually going to run into that situation very often where you're obscuring patterns by adding in more noise. I mean, I would say it is possible, I guess, if you're in a high dimensional setting to do that. Although it just if there's a strong enough signal there from the other things, I think that those noise features would wash out like you would expect them to.
Couple more right in this area. Is the inflated type 1 error rate a result of the Jeffreys-Lindley phenomena?
I don't know what that is.
I don't either, so we're
I
not going to
don't
be able
know.
to answer that question. Okay. How many original features were used? Does it work when you have a small number of original features? So this is still in that same section of adding, um,
Of adding additional noise features.
yeah.
Yeah, so in this setting, um, I should have maybe stayed on this slide a little bit longer. This is a really simple linear model setup. So we've got n equals 100, p is equal to 5. I have this s here because that was sort of more relevant if you're comparing this directly to the paper. S is just the number of signal features. So in this case, we start with just 5 original signal features. It's just a linear model, and that's where you're seeing all these. So you take 5, and then you're adding in, here you'd be adding 25 more on up to 250. So yes, I guess is the simple answer.
Okay. Okay. So still in this section, the wild bootstrap works by adding noise to
Mm,
observations. It recreates heteroscedicity.
yep.
Um, that's more of a comment than a question, but I'll give you if you want to comment on that, you can comment on that.
Yeah, that's a good point. I don't think it would I don't think it would necessarily have an outsized impact on the sort of testing results as long as if you were applying something like that, assuming you were applying it to both models that you were testing, I don't think it would significantly shift the results one way or the other.
Okay. So this question came in later, so it's towards the end, so I'm not just going back anymore. Can you explain
Sure.
why the method of randomization of replacement features matters for the hypothesis test?
So I guess that sort of has to do with part two. We did this idea of kind of how that shrinking is being affected. So basically, the idea here is we're saying um, the test here is basically just asking, is there a significant difference between these two random forests that I'm building? One of those random forests contains a bunch of extra noise features you can see here on the x-axis, and one of them doesn't. And so the kind of, I guess, preliminary thing to have in mind here is that the argument we're making is that those extra noise features can help to do some regularizing and help to improve the model. And so the model is being improved simply by virtue of being regularized, and that regularization is happening simply by virtue of having extra noise features. And so if I was to compare one model that contained a bunch of extra noise features, in some sense, it would be the equivalent of comparing two random forests with different values of mtry or something like that. And so if you think of it in those terms, then it might not be very surprising to know that those two different random forests have two different predictive accuracies. But in some sense, that is what you're testing here. And so the idea is that by doing a replacement test, you're keeping that dimensionality fixed. And so if you're replacing the features in question with, let's just call them sort of random noise replacements, then whatever beneficial effects you're getting simply by virtue of doing that extra regularization, you should be getting in both models. And so the hope is that that cancels each other out. And if there's actual further signal in those features that you're testing, then that sticks around while the regularization effects sort of cancel each other out.
Okay, you have more questions left than you have time to answer. So,
Sure.
so I'm going to pick, I think, two more. And then there's
Okay.
several people have asked if you're willing to share your slides at the end of the presentation.
Sure.
Are you willing for us to share
Yeah.
these through NIST? Okay.
Yeah.
So
Yeah.
if
Sure.
everyone's asking that, we'll make them available. So let me pick maybe one more question and then we'll let everybody go here. For large genomic data sets, e.g. 50,000 gene-related features per sample, should
Mhm.
one rather include all variables in a random forest or use a filter to one, reduce noisy features, or two, to filter out signals, e.g. differential expression filter?
I I I guess I sort of punt here and just said it would depend on what you're actually trying to accomplish. If you're saying I just want the most accurate model that I can get, then I would say why not start with all of them and just sort of see what happens and try. Yeah, I mean, there's no reason or there shouldn't be any reason why you couldn't just try both approaches and go with whichever one seems to be working. If you're relating that to this sort of context and you're asking, I have this big, messy, high-dimensional biological data set and I want to do some kind of testing, then I guess I would come back to what I was just alluding to and say, whatever kind of testing you're doing, you really ought to have some kind of randomized replacement in there in the second model as essentially just basically like a control on regularization to make sure that if you're seeing a benefit by adding certain features into the model, that benefit isn't arising simply by virtue of it regularizing the model in some unforeseen way.
Okay, well, Dr. Mensch, thank you. Clearly you had an audience that was very excited about this talk today. Appreciate your
Yeah.
answers to all these questions. And we'll be sharing the live recording on the NIST YouTube channel and make slides available through the NIST website. So thank you everyone for participating. And you still have 100 people online listening to your last few minutes. So really terrific talk today, and we appreciate it.
Yeah, thank you. It was an honor to participate. Thanks everyone for coming.
Thank you.
Thanks.